Hey everyone, thanks again for joining us on our next video in the weather and climate series. Before we begin talking about wind, which is the wind and air currents, which are the two main themes for today's presentation, or for this video rather, I want to start with something I forgot to end off with on the latitude and solar intensity video. And this is just a small little activity to get us thinking about insolation and basically what that means at different latitudes. So as you can see here, we have a graph with corresponding lines that represent different locations on Earth, and they're graphed by monthly values of solar radiation. So the question is, what locations do you think each of these lines correspond with? And if you want, you can pause the video and take a couple seconds to think about it, and I'll also pause for just a few moments before I give the answer. Okay, so starting with number one, we can see how basically from December or January till March, there's no insolation, and then from March it steadily rises up until June, where it peaks and then comes back down again in September. From September to December, there is no insolation. So we can probably guess that this is somewhere in the Arctic region, right? Because we're seeing that there's no sunlight from basically September till March, and then basically all the insolation happens in between the two equinoxes, peaking at the June solstice, which is when the northern hemisphere is turned towards or tilted towards the sun, and we get Arctic regions getting sunlight pretty much 24/7. So this is probably somewhere in the Arctic. We can see that number two is probably a little bit more southerly. We can still tell that it's in the northern hemisphere because it gets its peak insolation at the June solstice. And then it's not as northerly as the first line, because we still have a few. We do get a bit of insolation from January till March, and then September till December as well. So it's probably a little bit more southerly, but still in the northern hemisphere. Number three, again, probably in the northern hemisphere, since we see peak insolation at the June solstice. But also we have a substantial amount of insolation coming, in all other months. So this is, northern hemisphere, but probably more southerly than either the first or the second. Now the fourth line is interesting. We can see that the insolation peaks at the equinoxes and actually dips a little bit during the June solstice. And so what this tells us is that it's probably at an equatorial region. And that's because we can tell, so what happens at the equinox is that the Earth, you can imagine, obviously straight isn't really the correct term, but you can imagine that on its tilt, tilting back and forth on its axis, the Earth is basically straight, for lack of a better word. And so the peak insolation coming in at the equinoxes means that the most amount of sunlight is probably when it's hitting that equatorial band. And we can see it dips a little bit in June, so this is probably also a little bit in the southern hemisphere, just because the values for insolation are a little higher in the winter months than in June. Perfect. And our second activity is based on this picture here. So roughly, what time would it be in Mexico City at the time of the satellite image? How do you know? What time of year would this picture have been taken? So first, let's figure out where Mexico City is. I suppose, I'll pause for a moment or two, and you can pause as well to follow along. Okay, so first let's figure out where Mexico City is. So if you can see my mouse over here, Mexico City is basically this sort of area of light over here that's in Mexico. And we can tell here that the time of the day is probably late night or early morning. We can see that parts of North America are already a little lit up. And so, that means it's probably morning around, or late night, early morning where Mexico City is. What time of year would this picture have been taken? Well, we can tell that the Arctic region is pretty much totally insulated. Basically, seems like there's no darkness at all at any point during the day. Even any of these, the dark never touches the Arctic regions. So this is probably taken in the summer. Okay, following those two short little activities, we're going to talk more about wind. So you might be familiar, I guess, generally with the concept of wind. We all know what it's like when it's windy, but it's a little bit tricky to describe exactly what wind is. So wind is driven by pressure differences in the atmosphere. So heat causes air molecules to move faster, given their higher energy, and this movement spreads apart the molecules, basically reducing the density and pushing air up, which leads to low air pressure. I did briefly talk about this in our first video about basics of the atmosphere, so take a look there if you want a bit of a refresher on that. But basically, we can see that when air is less dense, it rises, and that leads to areas of low pressure. We can start by looking at the right side of this diagram. So we can see the L is basically area of low pressure, right? And then we see this warm air rising. And in turn, basically air from surrounding areas rushes in to fill that void. So you can see these arrows here basically represent air that's coming in to even out the lower air pressure here. So essentially, this movement actually creates wind. That's the flow of air rushing in from areas of from higher pressure to low pressure. But it can also work the other way around. For example, if we have high pressure air, basically this is air within a high pressure column, and as we know, high pressure air tends to sink. Basically, this displaces the surrounding air, which might be at a lower pressure, and basically displaces it outwards. So wind can be either high pressure air pushing air outwards, or low pressure air basically drawing air in to replace it. Essentially, that's what wind is. Talking a little bit about maritime winds. So wind is generally driven by what we call convectional flow patterns. And convectional flow patterns are the movement of air, as you can see in these two diagrams. Basically, as I mentioned before, from warmer, lower pressure areas to higher, colder or higher, cooler areas, basically generates this flow. Basically, the principle is with maritime winds is that during the day, water takes longer to heat up than land, which leads to air pressure differences, as I mentioned earlier, because of air rising and air falling. And so there's typically a region of lower pressure during the land. And as we know with wind, the air from a higher pressure region will flow to a lower pressure region. And that's basically these maritime winds. So like a sea breeze, for example. And then at the night, or during night time, water takes longer to cool down. So wind is going to flow in a reverse direction from the land. And this is typically why coastal regions, or regions that are situated closer to large bodies of water, tend to have more moderate climates due to their proximity, due to the moderating effect of the water. Cool. Now we'll talk a little bit about prevailing winds. And prevailing winds are the main or normal direction of winds that blow across the earth at any point in time. Basically, there are three core principles for how prevailing winds are generated in the Earth's atmosphere, and this follows what we call the Hadley model, which was developed in the 1730s, so quite a while back. And basically, there are three principles here that govern how prevailing winds work. So, convection currents bring warm air from the equator to the poles, and in turn, colder air gets generated at the polar regions. And then at the poles, so cool air descends, and that sort of increase in air pressure leads to air warming once again. And once that air gets warmed up, it rises and it flows down. And basically the cycle starts again once the air rises, and this generates a cell, essentially. So we can see here a description of two cells here, the two Hadley cells at different in the different hemispheres. We can see how this process works. However, one of the main complications with this is that Hadley's model doesn't account for surface elevation, continental shapes, ice and snow, and a whole range of other factors. And basically, later on, scientists realized that there are actually 3 cells in each hemisphere, so 6 cells in total. And basically, there are 3 different sets of cells. So we have here at the equatorial regions, we have the Hadley cells. At the mid-latitudes, we have the Ferrel cells. And the polar regions, we have the polar cells. And basically, they work the same way as, if there were only one Hadley cell. Warm air rises, flows, and then comes back down once it's cooled, and the cycle starts again. And basically, we can see that high-pressure areas generally coincide with the deserts in the world. So the final ingredient to explain prevailing winds is the Coriolis effect. And basically, the Coriolis effect states that winds are deflected towards the right in the northern hemisphere, and they're deflected towards the left in the southern hemisphere, and this is due to the Earth's rotation. And generally, the speed of the winds increases as we get closer to the poles, and the atmospheric circulation moves with the tilt of the Earth. So essentially, at different points in time, we have what's called the thermal equator, which is essentially where maximum amount of insolation is hitting the Earth at any point, and that sort of band is what we call the thermal equator, which is different from the geographic equator, which is always set at 0. But here's a helpful video to explain essentially how the Coriolis effect works. Let's take a look.
As well as being split into 3 cells, the global circulation pattern is at an angle due to the Earth's rotation. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and has moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere.
Yeah, so essentially, as you can see from the video, winds in the northern hemisphere are deflected towards the right, and in the southern hemisphere they're deflected towards the left. The general speed of the winds tends to be higher as we get closer to the poles, particularly in the southern hemisphere, where there's little land getting in the way of it. That's why we have higher speed winds at around the 40, 50, 60 degree latitudes in the southern hemisphere. Just to always remember, though, that, the one thing is that the Earth isn't static. It tilts year-round on its axis, meaning that the latitudinal equator, so essentially, the geographical equator at 0 degrees, isn't always going to receive the greatest amount of sunlight. So when you keep in mind, one thing to keep in mind is that we have a thermal equator, and this essentially shifts the wind systems either northwards or southwards along the surface during different points in time during the year. So a couple of important terms to recognize. First is the ITCZ, and this is the Intertropical Convergence Zone. And essentially this follows along the thermal equator, where the trade winds meet once again. It's an area of low pressure since warm air is rising, and it's generally subject to pretty unpredictable storms because the air is rising. Next we have the Horse latitudes, and these are around 30 degrees in between the Hadley cells and the Farrell cells. Basically, these are areas of high pressure with generally calm weather. Next we have trade winds, and these are the winds, trade winds and westerlies. They're generally winds are named based on the direction they originate, not the direction that they flow. And the trade winds, they're just so named because sailors and navigators would use them during the period of exploration, to speed up their travel. Next, we have the monsoon, and the monsoon is a seasonal reversal of the prevailing winds, which is often associated with tropical regions, especially in South and Southeast Asia. So again, this forms due to differential heating of the land masses. So in South Asia, for example, during the winter months, prevailing winds that are flowing from drier regions like Tibet and the Himalayas, they bring dry, warm winds to the region. But in the summer months, prevailing winds will actually flow from the Indian Ocean, and again, this is just due to differential heating in the atmosphere. And yeah, so we have what you might have heard of, which are called jet streams. Basically, storms, essentially, before we talk about jet streams, we should say that storms generally follow certain predictable pathways. Not all the time, but if we study weather maps over the course of weeks, we'll see that many of them do. And basically, jet streams, and basically these storms are due to jet streams. And jet streams are high-speed winds that circle the Earth, usually just below the tropopause. So that's basically the boundary between the troposphere and the stratosphere. They reach speeds of over 200 kilometers per hour and are typically hundreds of kilometers wide, flowing in a sort of ribbon pattern. There's two main streams. One is the polar front, and the other is subtropical jet stream. Basically, two of them exist in each hemisphere. So there's four in total. There's in total 4 major jet streams. And polar front is formed through temperature contrasts between colder polar air and warmer tropical air. So the air in colder polar regions tends to exert lower pressure at the same height than a mass of warmer air. Since the air is less dense at the same height, you sort of have more air pushing you down, and that exerts greater pressure. And it's this pressure gradient force that actually leads to winds. And these tend to be far stronger in the winter when temperature differences are more dramatic. So some weather systems tend to ride the jet stream, meaning they can be transported long distances, especially low pressure systems. For example, every year we tend to be hearing about polar vortices. Basically, they're systems bringing unusually cold air south, leading to heavy snowfall and chilly temperatures. And yeah, jet stream, as shown by its ribbon-like structure, you can see in the map there, can buckle and bend due to the movement of masses. Basically, rippling. There are some things that can ripple these air masses, that might bring different air masses together, creating fronts and even storms. So jet streams are generally sort of intense areas for weather formation. Yeah, and then a little bit about ocean currents. Basically, ocean currents generally tend to follow the path of prevailing winds. So as they move along, as prevailing winds move along the air, they sort of drag ocean water with them as well. And generally colder water that tends to be less salty sinks as hot salty water from tropical regions flows towards the poles to replace them. So as I mentioned, there were convection patterns in the air. There are also convectional patterns within the ocean as well. And cold water essentially makes its way to the equator over long periods of time. And these occur, again, in convection currents. So the two main things are these ocean currents are driven by salinity and temperature, and the differences in that. And again, of course, the Coriolis effect generally determines their path, as well as ocean topography. So depending on how shallow and how deep the ocean is, that'll change the movement and, and characteristics of the currents. So a quick little activity before we finish off. From what direction do you think the prevailing winds are blowing across Fiji? So again, I'll give you a couple of minutes to pause and think about it. Okay, so we can see that across Fiji, the winds, so Fiji is located below the equator in a tropical region, so between 10 to 20 degrees south. And we can see that the winds that are blowing across Fiji are likely to be blowing from the east. So we can see here, there's a region of high pressure, here there's a region of low pressure. Generally, these winds we can imagine will be flowing in a westerly direction, but from the east across Fiji. And if we go back to the map, we can see that at these latitudes, the air generally tends to be flowing from the east, from the southeast to the northwest. And last question: in which areas do you think the ship experienced the highest wind speeds and the lowest? So basically, this map is just showing the path of a ship taken. So why don't we take a couple of minutes to figure out where the ship experienced the highest wind speeds? Okay, so we can see that the ship had probably experienced the highest wind speeds around sort of the 40s, 50s, and 60s latitudes. Again, that's just due to the convergence of air masses, things like the jet stream, little land getting in the way of air flowing across the Earth's surface. So this is probably where, like around the Indian and Southern Ocean, that's probably where the ship experienced the highest wind speeds. In terms of the lowest, generally around the the doldrums area, so around 30 degrees of latitude, it's probably where the ship experienced the lowest wind speeds. Okay, thanks everyone.